Hello everyone, this is section 2.4, Mechanical Vibrations, which is an application to our solutions to the differential equations we've been studying, in particular second order linear homogeneous differential equations with constant coefficients, as we're going to see. But before we start talking about the theory of mechanical vibrations, I feel it necessary to review a few concepts from trigonometry that you probably haven't seen in a little while. So the last time you saw the cosine of the difference between two angles was probably in a pre-calculus course, and I don't think you spent very much time on it, but here's the identity. Cosine of p minus q is cosine p cosine q plus sine p sine q. And in the example, basically just have to identify this in reverse. Notice how the 45 degrees is behaving as the P and the 30 degrees is behaving as the Q. And so therefore it's fitting the form, and that results in cosine of P minus Q, or in this case cosine of 45 degrees minus 30 degrees, or cosine of 15 degrees. This was actually how we used to find the exact values for trigonometric functions of angles that were not multiples of 30 and 45 and 60, was to use these identities. So now you could find the exact value for cosine of 15 if you wanted to. But in any event, second identity we'll need is the cosine of a negative angle. Sometimes we say cosine is an even function because the cosine of a negative angle is the cosine of the angle. And so, for example, the cosine of negative 45 degrees is just going to be the same as the cosine of 45 degrees. That one's actually easy to verify because if you think about the cosine function in the first and the fourth quadrants, if you have an angle in the first quadrant, cosine is adjacent over hypotenuse, and here's the adjacent side if you form a right triangle here, and of course this is the hypotenuse. And if you have a similar right triangle in the fourth quadrant, cosine is adjacent over hypotenuse, so it's the same adjacent, same hypotenuse, because hypotenuse is always positive. In any event, you don't have to worry about where it comes from, but just the cosine of a negative angle is the same as the cosine of the angle. Here's actually what we'll be manipulating. We're going to end up with cosine of, this is Greek letter alpha, as I'm sure you're familiar with, and then the W is lowercase omega. So that's omega sub 0, and then times t. What we're going to be able to do is actually reverse these, because what we could do is we could say this is the same as the cosine of, if I factor out a negative 1, I can then write this as negative alpha plus omega sub 0 t, and then go further to write it as the cosine of minus, and then I'll write this omega sub 0 t minus alpha, but now it's fitting the form of cosine of minus this angle, so that's the same as the cosine of that angle, omega sub 0 t minus alpha. So that's showing it literally. We don't have to show those steps every time. We just realize reversing the order is allowed because it's just the opposite, and the cosine of the negative is the same as the cosine of the positive. But that's the theory behind why it works. Okay, so this is basically what we're going to be doing. We're going to be transforming a function, x of t, so x is given as a function of t, into this special form of c cosine omega sub 0 t minus alpha. And the significance of that will become apparent when we start talking about the theory behind mechanical vibrations. So we start with the given x of t is 5 cosine of 2t minus 12 times the sine of 2t. And what we're going to do is we're going to make a sketch. And we're going to consider this equation as fitting the form of x of t equaling a times the cosine of omega sub 0 t plus b times the sine of omega sub 0 t. And so our values of a and b are the coefficients of the cosine and the coefficients of sine respectively. So a is 5 and b is negative 12. And then we're going to make a sketch of a right triangle where we consider the horizontal axis as the a-axis and the vertical axis as the b-axis. And I kind of made this such that I already knew I was going to be in quadrant 4 because a is positive and b is negative. Now it's just a sketch, so it doesn't have to be accurate in terms of the scale. So I'll just say that's 5. This is negative 12. So that's the point. And then here's my right triangle. Remember, always drop it perpendicular to the x-axis. So I'm going to label this as theta, but this is the actual, our reference angle. That is the angle the terminal side makes with, in this case, the a-axis. But this angle is actually the angle alpha. Alright, so we have that this horizontal leg A is 5 and the vertical leg B is negative 12. And we want to find the hypotenuse C. So the hypotenuse C is equal to the square root of a squared plus b squared. So that's the square root of 5 squared plus a negative 12 squared. So 25, 144, square root of 169, which is 13. And then also what we want to do at this point is find the cosine of the angle alpha and the sine of the angle alpha. And for reasons as we'll see momentarily. And the cosine we know is adjacent over hypotenuse, so that's going to be 5 over c, which is 13. And the sine of alpha is opposite over hypotenuse, so that's going to be b over c, or negative 12 over 13. And then in order to find the angle alpha, you could do it in many ways. What I like to do is consider that the tangent of theta, or the tangent of alpha, let's say, actually, let me say the tangent of theta. I'm going to find the reference angle first. I'm going to say it's the absolute value. Tangent is opposite over adjacent, so negative 12 over 5. So then theta is going to be the inverse tangent of 12 over 5, which comes out to 67.38 degrees. And we always want to give this in radians, so we're going to multiply by pi over 180. And that gives us 1.176 radians. Now that's the angle theta. So the angle alpha, since we're in quadrant 4, alpha is going to be found by taking 360, or 2 pi, because we have to be in terms of radians, minus theta. So minus the 1.176. And pi you want to express as 3.141592, etc. Use pi on your calculator to ensure accuracy. Into 3 decimal places, 5.107. And again, that's radians. Okay, so now we have everything we need from the triangle to go back to our expression, x of t equaling 5 cosine 2t minus 12 sine of 2t. And the neat thing about what we're going to do is we're going to factor out the value of c. So whatever the value of the hypotenuse is, we're going to factor it out. Now this might seem awkward, but it's really rather easy. What's awkward about it, how do you factor a 13 from a 5? Well, just think about what you need here to multiply by 13 to give 5. And that's just 5/13, because then the 13s will cancel and you'll get the 5. And similarly, think about what you have to have here in order to multiply by 13 to give negative 12. And that would just be negative 12 over 13. Because then again, the 13s cancel and you get negative 12. And then we have times the sine of 2t. Now, the significance of that is the fact that now, and this is why earlier we calculated the cosine of alpha and the sine of alpha, because now the 5/13 is the cosine of alpha and the negative 12/13 is the sine of alpha. So therefore we could write this as x of t equaling 13 times, and then this would be cosine alpha cosine 2t plus, because the negative is part of the sine of alpha, so plus the sine of alpha times the sine of 2t. But then we recognize what we have in parentheses as fitting the form of the identity for cosine of p minus q. That is, the alpha behaves as our p, the 2t is our q. This is cosine p cosine q plus sine p sine q, which is cosine p minus q, or for our situation, cosine of alpha minus 2t. And then what we're going to do, because we want the t first, that's really the omega sub 0 t, is use the cosine of the negative angle, like we had verified up here, to switch the order. So then this becomes 13 times the cosine of 2t minus alpha, and now we'll replace alpha with its value, which was 5.107. So we've got x of t is 13 cosine of the quantity 2t minus 5.107. Okay, now the significance of having that form is going to be illustrated by simple harmonic motion, and we'll get to that in a little bit. But let's start talking about the theory of mechanical vibrations. And there's basically four types of motion. When we talk about mechanical vibrations, we're talking about basically attaching a mass to a spring. And the four types are undamped, damped, undamped, underdamped, critically damped, and overdamped. And so we'll draw a little sketch of the scenario. Basically, consider a frictionless horizontal plane. So let me just draw a little plane here. This will be my walls and the floor, if you will. And another wall over here. And we'll attach a spring. That's how I'm going to draw my spring. And there's going to be a mass. Attached to the spring. And also, we're going to consider having this little unit, which is going to be like a shock absorber. And that's going to be what we call our dash pot. So there's like a little, maybe a little plunger in here, right, that's absorbing the shock. So you got the mass attached to that. And then we'll have that attached to the other wall. So we've got our mass, spring stretched out. Let's say the spring has equilibrium here. And then this distance is the distance that the spring was stretched out. So we'll call that x, maybe x sub 0, right? All right, so that's our scenario. And the dash pot, we're going to label with a value of c. And as mentioned down here, its resistive force is proportional to the velocity. Okay, so that's the scenario. Now let's talk about the physics behind this. We have Hooke's law. So Hooke's law has to do with the spring. So the restorative force that the spring exerts on the mass is proportional to the distance it's stretched. I guess we're just calling it x instead of x sub 0. So we'll say F for force, S for spring is proportional to, okay, we're going to say negative kx, because if x is less than 0, so if x is negative, then it's compressed, the spring, and if x is greater than 0, then the spring is stretched. So if the spring is compressed in that direction, it's going to have a restorative force that's positive, because x is going to be less than 0, which would make this negative, and the x that's negative a positive. And if it's greater than 0, the value of x, then it's stretched out, so then the force is going to go to the left. And that's where k is the spring constant. And then we have our dashpot. The dashpot, like I mentioned, is a shock absorber, and it has a force that's directed opposite to the motion of the mass, and its restorative force, we'll just call F sub r, is proportional to the velocity of the mass. So if it's proportional to the velocity of the mass, then it's equal to some constant times the velocity. And again, we'll do the negative, we'll take it negative to be negative c, where c is the damping constant of the dashpot. So that's going to be given. So depending on how you design the dashpot or your shock absorber. You can add an external force if you wanted to. In our situation, we're really not going to see an external force, but if you do add one, the total force is going to be the sum of the forces. So the force due to the spring plus the force due to the dashpot plus the external force if it exists. And then we know Newton's law. Oh, the one thing I forgot to mention here was note that the velocity is the time rate of change of the distance, so dx dt, or you can call it x prime of t. Then we know Newton's law, sum of the forces is mass times acceleration, but the acceleration is the second derivative of position, x, with respect to time, or x double prime. So then it would follow that the force mx double prime is equal to, so this is our force, which is equal to the force of the spring plus the force of the dashpot plus the external force. We'll just call that uppercase f of t. And then if we bring the negative kx and the negative cx prime to the left, we have our formula. Which is a differential equation, note with constant coefficients, m, c, and k. Now the f of t is going to be 0. In our case, later on, we'll see a situation where f of t is not 0. And that will make it homogeneous. If c equals 0, then there's no dashpot. So you've got no shock absorber if you let c equal 0. And that's what we call undamped. So by damped, we mean, add something in there that absorbs the shock. But if you let c be 0, you don't have a dashpot. You just got a mass in a spring. Like, for example, consider a mass suspended vertically on a spring. So let's say, here I'm going to draw my figure starting up here. I'll say this is my ceiling, and let me say that this is just the spring hanging out, unstretched. And then you attach a mass to it. Okay, and that would be equilibrium, static equilibrium at that point. Obviously, it's going to stretch the spring. and then let's say you pull down on the spring, you pull down on the mass, stretching out the spring even further, and then you've got the system, let's say, in motion. So with that situation, and it could be the horizontal situation as well, but this was easier to kind of describe. We've got my double prime, notice how we changed to y because it's vertical, plus cy prime plus ky is f of t. But if we want free undamped motion, then we're considering a horizontal surface where we're letting the dash pot equal 0 and the external force equal 0 as well. So our equation here is basically letting c equal 0 and f of t equaling 0 just becomes mx double prime plus kx equaling 0. And then if we do a little algebra, we divide by m, and we define omega sub 0 as the square root of k over m. That would mean that if you square omega sub 0, it would be k over m. And so we replace omega sub 0 by k over m. Omega sub 0 squared, excuse me. We replace k over m by omega sub 0 squared, and then we get this equation. X double prime plus omega sub 0 squared times x is 0. And we could write the characteristic equation, which would be r squared plus omega sub 0 squared is 0, and then find the roots. So if you have r squared plus omega sub 0 squared equals 0, omega sub 0 is a constant, so r squared would be negative omega sub 0 squared, and r would be, take the square root of both sides, plus or minus the square root of negative omega sub 0 squared. So that's plus or minus square root of omega sub 0 squared is just omega sub 0, but there's a negative under the radical, and the square root of negative 1 is the imaginary unit. And then a general solution for that would be x of t equaling e to the 0 t times cosine omega sub 0 t let me say it this way, c1 cosine omega sub 0 t plus c2 sine of omega sub 0 t. And then we'll just, e to the 0 t is just 1, and if we replace c1 and c2 by a and b respectively, here's our new equation. And notice that that's the equation that we started with on the previous page, where we were able to transform it into the following form by our identities. Okay, so that's the idea. And now we're going to look at, in particular, we're going to continue this theory, and we're going to consider our general solution. And we're going to transform it using the general properties. Now, we already saw how to do it. We're going to transform it in general, that is. We already saw how to do it for specific values of a and b and omega sub 0, but now we're going to consider in general, trying to obtain this form so that we can analyze the motion. And we'll, at the end here, show the analysis of the motion. So we start with the given equation, and we choose c and alpha so that c is the square root of a squared plus b squared, and cosine of alpha is a over c, and sine of alpha is b over c. If we wanted a little figure here, for simplicity, I'll just draw a right triangle, not in any specific quadrant. And let's say this is my angle alpha. Then, as we had done in our example, we'll take A to be the horizontal leg, B to be the vertical leg, and C to be the hypotenuse. And then these follow. C is square root of A squared plus B squared. Cosines of alpha is adjacent over hypotenuse, A over C. Sine of alpha opposite over hypotenuse, B over C. Now, the way the textbook does it is this. When we talk about the tangent of an angle, and we want to, if we just talk about the tangent of some angle alpha, it can be between 0 and 2 pi. And it's not restricted to this. This is the range of the inverse tangent of x. So you might recall that the inverse tangent is restricted between negative pi over 2 and pi over 2. So if we're going to use the inverse tangent, this is what the textbook does. They say inverse tangent of b over a if a is greater than 0 and b is greater than 0. And what we're doing here is considering the Cartesian system, but again with the horizontal axis being the a-axis and the vertical axis being the b-axis. If a is positive and b is positive, we're in quadrant 1. So you're just going to get the angle in quadrant 1. If a is less than 0, you're either in quadrant 2 or quadrant 3. Let me use arrows here. You're in quadrant 2 if b is positive, and quadrant 3 if b is negative. But that'll give you a negative angle, so that's why we say pi plus that angle. It'll give you a negative value if you're in quadrant 2, because all students take calculus, that's where the trig functions are positive. So tangent's going to be negative there, so if we add that negative angle, we'd end up in quadrant 2. But then tangent's positive in the third quadrant, so if we add that angle, that's why this formula works, we're in quadrant 3. And then this would be the situation where A is positive and B is negative. That's quadrant 4, which is going to be a negative value of tangent. That's why we say 2 pi plus that angle, because then that brings us into quadrant 4. Now, you could do it this way. This is what the textbook does. But the way I did it earlier is I took the absolute value and found the reference angle, and then based on the quadrant, determined what the actual angle was. So if you want to use these formulas, that's fine. But you see what we do next, is we start with our standard form again. We factored out the c. So notice how we just put a c in the denominator of each. And then these values, a over c and b over c, note that they were, just as we did in our example, they're the cosine of alpha and the cosine of beta, and the sine of alpha respectively. So we replace those, and I made the note here, and then we use our identities to rewrite it so that it's the cosine of, this would be alpha, this is our P, this is our Q, here's our P and our Q. So we use that identity to get cosine of alpha minus omega sub 0 t, and then we switch the order, that's the cosine of the negative angle, to finally get the desired form. And the reason why we like this desired form is because that's simple harmonic motion. And basically, excuse me, what we have is, say, a vertical axis, horizontal axis, call it T. Vertical axis we'll call X, because it's X as a function of T. You've got the amplitude, C, of the cosine function. So that would be C and negative C. Maybe it doesn't start exactly at C. Maybe there's a little shift. Maybe the graph hits its high point, let's say here. Okay, that might be what the graph looks like. I think I went a little too high there. See if I draw a horizontal line, yeah. Let's fix that. Okay, so there's our cosine function. If we draw vertical lines at the two peaks, that's going to be the period. T. And that distance where there's the little displacement, that's going to be delta, what we'll call delta. That's our phase shift, or phase angle, or time lag. And this is the graph, of course, of x of t, equaling c cosine omega sub 0 t plus or minus alpha. And so then we have the characteristics described here. The amplitude is c. You got the what we call the circular frequency of omega sub 0. The phase angle is going to be alpha, which determines the time lag, alpha over omega sub 0. And then we have the period defined as 2 pi over omega sub 0. And the frequency is just 1 over the period. Alright, so that's the analysis. And I think we'll look at the first question, just to get this out of the way. And it says to determine the period and the frequency of simple harmonic motion. So that's what we just got through discussing. Of a body with a mass of 0.75 kilograms on the end of a spring with a spring constant of 48 newtons per meter. So this is not the type of thing I'm going to ask you on the exam, but using our formulas, let's go for the frequency first. Using our formulas from simple harmonic motion, the frequency omega sub 0 was initially defined, if we look back at the first page of our notes, We had initially defined omega sub 0 here to be the square root of k over m. So that would be the square root of k is the 48 newtons per meter over the mass of 0.75 kilograms. And in terms of the unit conversions, Newton per meter over kilogram. Okay, a Newton is a kilogram meter per second squared over meters over kilograms. And so the kilograms cancel, the meters cancel, everything replaced by ones formally, of course. And we get 1 over second squared. So this gives us the square root, 48 over 0.75 is 64, and that would be 1 over second squared. So that would give us 8 times 1 over seconds, which we could say is 8 radians per second, because remember, radians is a pure number. And that's the same as we convert that to pi radians is 1 cycle, 1 revolution, and we get 4 over pi cycles per second, which is 4 over pi hertz. Okay, so don't worry about any of that physics. There's just 1 or 2 questions in the homework that have you pick out the formulas and do some manipulations, so that's why I'm going over this one. But then once we have the frequency, we can get the period, because the period t was defined to be 2 pi over omega sub 0. So that was from our graph here. T is 2 pi over omega sub 0. So 2 pi over 4 over pi. And let's rate it as cycle 1 over seconds. Number of cycles per second. And then, oh, I'm sorry. Let's take it at, 8 times 1 over second. Because I want the period to be in seconds. So we get pi over 4 seconds. Okay, so again, that's kind of the physics behind it. And we'll come back for the example, the next example, and that will be the type of thing that you'll expect to see on an exam. All right, so we'll see you when you're ready for part 2 of this discussion.